Il serrato gioco di concetto astratti così caratteristico della moderna algebra che rende quest'ultima di difficile lettura. We do not find in this book those terrible aspects of modern algebra which render modern algebra so difficult to read. That is, he really is an Italian now. He is absolutely even acceptable to Italian geometers. Comunque sia il notevole libro di Van der Waerden agevolerà senza dubbio la conoscenza dei metodi della scuola italiana e cooperare ad una reciproca comprensione tra I geometri italiani e gli alibristi tedeschi. So the goal promoted by this book is friendly and understanding collaboration between, on the one hand, the Italian geometers and on the other hand, the German algebraists. This is where we are in 39.
By the way, this book was required reading from Matsusaka's students in algebraic geometry in Brandeis.
Which year?
Oh, certainly through 1985.
Okay. Well, okay, so this book was not forgotten, at least not in Brandeis. Okay, I didn't know this. But it does look, you agree, I mean, it does look surprising when you look at it from today's vantage point. So what does all this mean? Well, one sort of warning note I should just sound, and this is a handwritten transparency, just put in there as a safeguard so that nobody will criticize me on that afterwards, is that if you really want to understand what's happening around Van der Waerden in the 1930s as far as algebraic geometry is concerned, you have to look at Severi. That is not easy. There's more than one of the 6 volumes of his collected papers, just papers written in that period. And he is very productive. It is not as if the algebraic geometry only has produced trash in the 1930s. So I know exactly one attempt, sort of more or less historical attempt to at least try to do some justice to this production. That is in this thing here by Ciliberto and Brigaglia, the Italian algebraic geometry between the 2 world wars, where they point out in particular seminal ideas brought forward by Severi, not just going through all the papers, but just sort of classifying curves. For example, the variety V and delta, classifying curves of degree n with delta nodes, or his forthcoming and very rich ideas on different equivalence relation on cycles, which is actually something where a strong collaboration and almost competition arises with Van der Waerden, and Van der Waerden together with his most famous and successful pupil, Chow. So in order to really come to grips with this period, somebody would have to do the enormous job of making a thorough historical study of not only Van der Waerden's papers, as you see them on the left, but also all of Severi's production and see how they mesh together. I have not done this, and it's quite a heroic task, I think, before us. So this was the first sort of brief story I wanted to tell. Now I turn to something else, which, however, is, as you will presently understand, very much related to the story I was just indicating. So there is one other subject, very important in the 1930s, in particular in Germany, which calls for a rewriting or an extension or a generalization of algebraic geometry. And that subject is the Riemann hypothesis for function fields over a finite field, or as we say today, for curves over finite fields. So without going into the technical details, if I try to do this, I would not have time at all to finish my talk. Let me just say that this is an analog of Riemann hypothesis for the L function of such an object, a curve over a finite field. And curves have a genus, and for genus 0, there's really not very much to do. But for genus 1, this is a very interesting theorem, which was proved in 2 ways, actually, 2 different proofs given at a distance of 1 year by Hasse in 32-33, or 33-34 published. And so this is the genus 1 case of the Riemann hypothesis. So after this, the open problem was how to prove the Riemann hypothesis for curves over finite fields for a curve of any genus, higher than 1, curves of higher genuses. And so now I'm going to flip by very quickly, don't be frustrated, some slides with lots of text on them, and I just point out certain things because it's really another story, but I have to run it by you very quickly in order to point out a certain number of things. So the basic idea how to attack this problem was provided by Doering and first communicated by Doering on 9th of May 1936 to Hasse. The idea was, when you look at the proof that Hasse had given in the genus 1 case, you use endomorphisms of the elliptic curve, the genus 1 curve in question. There you have a notion of endomorphism. In higher genus, you don't have endomorphisms. What are you going to replace the endomorphisms with to start doing your proof? You replace them by correspondences. This was Doering's idea. So a theory of correspondences existed, in particular explained in Severi's textbook, Trattato. But of course it existed only over the field of characteristic 0, over C, in this Italian tradition, and so the necessity arose to systematically develop an abstract algebraic geometry which would also work over finite fields, putting up the whole theory of correspondences, proving all the standard theorems, so that then you could deduce from that the Riemann hypothesis, something that the possible strategy was seen immediately by Hasse, as he indicates in his first reaction. Now, Wey comes in because Hasse and Wey correspond at the time. So anyway, I spare you this. There's well, okay, never mind. So Wey, Hasse, Doering, and another Wey, okay. And then this is where I stop. From January 6 through 8 of 1937, Hasse organizes a conference on algebraic geometry in Göttingen. What was the idea of this? The idea of this was to do for algebraic geometry what the Schief Congress that we have heard about the day before yesterday did for the theory of central simple algebras. Remember this congress that Hasse, very young at the time, when was it, 28 or so, organized in Marburg. 31, I'm sorry, still young. 31 organized in Marburg with Brauer and Noether there and so on, where all these developments that we heard about the day before yesterday came from. This was an extremely successful meeting because what did it do? It brought together a small group of the main actors in this field, and they could talk to each other and therefore get to the whole theorem that then was published. And so Hasse had the idea, after this idea of Doering and so on, to bring together all the experts on algebraic geometry. So, well, Doering was in there was van der Waarden, there was Geppert, there was Jung, names that you don't necessarily know, but in Germany at that time were certainly considered to be in algebraic geometry and active in this field. He also, Hasse, invited André Wey. He invited André Wey, and André Wey didn't have to think very long. He said, I cannot come, because that's exactly when he was going to Princeton. He was spending half a year, the first half year of 1937 in Princeton, and he already had left Europe before that date. So he couldn't come. The question is, had he not gone to Princeton, would he have considered going? He says in his autobiography that after the Röhm Putsch, after May 34, he did not go into Nazi Germany any further than the Black Forest to hike with Siegel. And so if that is true, what he says in his autobiography, he would have never considered accepting this invitation. As it turns out, he didn't have to think about it because he wasn't there anyway. So there is an attempt on Hasse's part to do sort of this, to make this development, and this bringing together of important people, and the same thing continues now in collaboration with the Italian side. Just as I indicated this close contact between van der Waarden and Severi, this generalizes to the Hasse school. So, for instance, there was the famous Volta Congress in 1939. Well, it actually wasn't there. It's one of those congresses, I think it's a rare example of a congress of which the proceedings exist, which has never physically taken place. It was cancelled for some administrative reasons, but since people had sent in their papers, they got published as the atti, as the proceedings of this Congress. So the Congress exists in the form of proceedings. And this was, Hasse submitted to this Congress. He couldn't give it because physically it didn't take place, but he submitted this paper written in it, translated for him into Italian. The goal of which was to sort of teach the Italian geometers the basics of what was needed for the algebraic geometry for curves over finite fields. This was sort of the idea. So to bring these two schools with their respective capacities together. And what about van der Waarden? Well, as I learned from, now I have probably placed this at the wrong place here, this transparency. As I learned just 2 weeks ago, when I was once again sitting in the van der Waarden Nachlass in the archive of the ETH in Zurich, van der Waarden, I can't find it, so I just tell you instead of losing time looking for the transparencies. Van der Waarden received the invitation to this Congress too late. Now, in fact, that didn't matter because the Congress didn't take place, but it was a systematic phenomenon. It did matter because it didn't contribute to the proceedings. But in a sense, it was a systematic phenomenon, and as he tells Hell Braun in a letter, which is in the van der Waarden Nachlass in Zurich, he systematically either received invitation to international congresses too late, so he couldn't go, or if he received them in time and applied to go, he was denied permission to leave the country. So the ministry clearly kept him in Germany. And van der Waarden's interpretation of this is that there was a note in his personal record in the ministry about his participating in the 1934 Congress of the German Math Association in Bad Pyrmont, which was the famous Congress where Bieberbach's attempt to take the whole German Math Association as its new Führer was averted. And van der Waarden was in the anti-Bieberbach camp in that Congress. Another interpretation is possible. This is just the way van der Waarden himself saw it. Maybe, as Günther Frey suggested to me when I talked to him yesterday, it was that the ministry did not like the fact that he never had accepted German citizenship. He was still a Dutch citizen, and maybe for that reason they created problems. Be that as it may, he had problems. He was not allowed to freely exert his international contacts the way he wanted. So now I see that the transparency was right here at the right. Okay, anyway, so I just told you what's in this letter. Well, actually not all of it, but it doesn't matter. So what do we learn from this? We learn from this that in Europe, the most active algebraists interested in algebraic geometry, and in particular I mean by that the Hasse school and van der Waarden, enter into an alliance with the Italian School of Algebraic Geometry and its uncontested leader, Francesco Severi. But this attempt at a collaboration was not as successful as one might have thought or might have hoped, especially if you compare it to what Wey and Zariski realized. The methodological paradigms of the two schools were quite far apart, and institutional and political impediments played a non-negligible role, at least between 1935 and 1945. On the other hand, the two people whom Mumford mentions in this quote and who clearly stand out as those who realized this enormous evolution and development and upheaval of algebraic geometry, Wey and Zariski, did their work and did their foundational work only once they were in emigration. Of course, Zariski left Italy very early. This is probably what Silke is going to tell us in the next talk, so I won't talk about Zariski. But with André Wey, the interpretation that I can give is very clear. As you probably know, regarding the Riemann hypothesis over finite fields, he published an academy note, which he wrote in the prison in 1940, where he claims to have essentially a proof of this, but an essential lemma remains without proof, the positivity of the trace. And in fact, everything that is in this note of 1940 was explicitly present in the discussions in the Hasse School in 1935. Everything. What Weil adds to this, the enormous generalization to give the whole Weil conjectures with, in particular, also the topological part that you, Colin, insisted on so justly yesterday in your talk, plus the whole foundational work that finally, in 46, led to the publication of the Foundations of Algebraic Geometry, all this breakthrough was realized only when he was in the United States. So if you look at it, and I don't think I'm wrong, I mean, it gives the impression that once you liberate yourself also geographically from the presence and influence of the Italian school, in particular as represented by Severi, you can think more freely, and sort of the possibility is there to think of a way of rewriting algebraic geometry which is much more fundamental than what van der Waarden ever tried to attempt during the 30s and 40s. And this, I think, is the reason why van der Waarden's name, much to his own regret, he expressed this several times also in letters that are in his Nachlass, is not remembered for his contributions to algebraic geometry today, but is remembered for his book Moderne Algebra. So now I will show you a very complicated slide, which I will turn around in many ways, trying to put, this is sort of an attempt one shouldn't make, but anyway, trying to put all the actors that I think are somehow important on one slide. So here you have Severi, which I have mentioned and insisted on. You have, on the other hand, Zariski, whom we are going to hear about, so I'm not going to say anything there. Then I turn around here. You have Gröbner. Gröbner in Germany in the 30s, in a way, is somebody who is very much close in spirit, on the one hand, to the Italian school, on the other hand, to ideal theory. And there is a correspondence in the van der Waarden Nachlass in Zurich between Gröbner and van der Waarden, which almost, I mean, I should be maybe a little careful, especially because this is taped on videotape, but it looks like, I mean, it reads almost like bickering. I mean, it's really, I mean, there are these petty discussions about should one use ideal theory, should one not, and so on, and it's, anyway, so he also published a book on algebraic geometry, but only after the war. Then there is van der Waarden, and I talked about him. I talked about his different periods as far as algebraic geometry was concerned, and mentioned the Chow coordinates as something which is, of course, a lasting contribution, but also linked to the name of his student. There is Geppert, who acts mainly as a translator because he knows Italian just as well as German for the Hasse School. There is Deuring, whose role with the correspondences. So now you see I turn over to the arithmetic side. I mean, with Deuring, I'm already in the arithmetic. These are people who are in the past. Then there is the Hasse School, in particular, as far as this theme of Riemann hypothesis is concerned, with his collaborator H.L. Schmid, who at the time was still in Göttingen, who rewrote practically Deuring's manuscripts in order to make them fit more with the paradigm of presentation of the Hasse School. Then there is Weil, who is, of course, one of the main actors, and I have talked about him. Well, I mean, he has an interest which is slightly different from the German school. Maybe I should say this. I mean, both of them fall under the heading arithmetic approach to algebraic geometry, but the arithmetic approach that Hasse and so on use is more or less directly coming from Dedekind and Weber, I would say, whereas Weil, in his spirit, is somehow more reminiscent of Kronecker, and this is already brought out very early by his 1935 paper on the arithmetic of algebraic varieties, where he implicitly also defines the notion of normalization of of normalized projective variety. Okay, and then the story ends, of course, as is well known, with the 40s. So, but there are other people here on that side of the slide. There is Kähler, who also in this time and way until the 40s, whenever he publishes on algebraic geometry or on geometry, uses the Italian language, not German. There is Helmut Kneser, and then there is somebody I do want to say something about, and he is rightly next to Zariski, and maybe Silke will say something about his role too. That is Krull. I mean, Krull is, of course, an algebraist, as you all know. He has been mentioned before. And he supplies in various papers, for example, it already is indicated in his introduction to his Ergebnissebericht of 1935 about ideal theory, but then more clearly indicated in later papers. For example, in this paper from 1937, he has a very peculiar distinction between multiplicative and additive ideal theory. And by multiplicative, he explains he means an ideal theory which is sort of directly coming from Dedekind's ideas about decomposing ideals and Dedekind domains into product of prime ideals. And then he will call arithmetical all those approaches to ideal theory and thereby also to algebraic geometry, which are in the spirit of multiplicative as opposed to additive ideal theory. And this is the use of arithmetic, which one finds again in Zariski. This terminology already very clearly shows that Krull had a different approach, did not immediately belong or cannot immediately be counted as a member of the Hasse school. So he is, in my diagram, he is very close to Zariski. He is somewhere else. He is independent in his way of thinking about these things from the others. And even though he stays in Germany, of course, keeping a relatively low profile, I guess, as far, because one really doesn't know very much about it, has direct influence on those actors, Wey and Zariski, who then rewrite algebraic geometry. Okay, now let me return to van der Waarden. Return to van der Waarden in October 1941, so we are now on the next page of the table of contents of this book. So we are here. This is when, at the annual meeting of the German Math Association, van der Waarden gives, as he says, an account of more recent American research on the question of, in this case, desingularization. This is about Zariski's paper, which we're going to hear about. And in particular, the fact that the notion of valuation, Bewertungsbegriff, has played a fundamental role. So van der Waarden is, of course, somebody extremely flexible who immediately picks up on these developments that are realized in the United States and then tries to explain them to the German audience, trying as far as possible to underline analogous work that has already been realized in Germany. So, for example, he quotes Jung and Kneser when he explains Zariski's local uniformization theorem for the resolution of singularities. So he picks up on this, and indeed, he continues to do so. He continues to do so on all sides. This is typical of van der Waarden. So, for example, if you look now just after the war, in 1947, there is one paper about divisor classes in algebraic function fields. So this is somehow a leftover from the war, I would say, in the sense that from his close association with the Hasse school and their attempt to communicate with the Italian school. So he writes his own presentation of algebraic geometry the way the Hasse school liked it to be formulated when dealing with curves over finite fields. On the other hand, that was 47. On the other hand, more or less as soon as André Wei's book, Foundations of Algebraic Geometry, comes out, he immediately reviews it. I'm not sure whether this is 48 or 47, but maybe it was printed late. But I mean, it looks like a more or less immediate reaction to the book. Publishes this review in English in the new Archival for Biskunde, and brings out very clearly the points that he likes, the positive points, and is willing to adopt more or less the new viewpoint of proposed by Wei. Not only this review, but he publishes in 1958, that's considerably later, but has the advantage of giving us some idea of how he looked back on all these developments 10 years afterwards, gives this address about André Wei's new foundations of algebraic geometry, which in principle is positive. He just tries to also make some comments about his own findings. Whereas, for example, this is a letter from Hasse to van der Waarden, which is in the Nachlass, where he recommends van der Waarden that he invite to Göttingen Roquette, who has just done in his dissertation an arithmetic proof of the Riemann hypothesis. This was after the war, after André Wei had published his proof, whereas Hasse, for example, at this date, in 1952, still writes that Roquette's proof is so nice because he, with this proof, you don't have to read this highly complicated book of André Wei. So this is not necessarily van der Waarden's reaction to all these developments. I think I have to, oh yes, I already went over time. I'm very sorry. I have to close. Just to recall my basic thesis in what I was trying to defend, it is not a one-way road. And the way it really happened, the way with this sort of sharp rewriting of algebraic geometry realized in the United States, is not alien to the fact that people had to emigrate from Europe and worked in this kind of isolation. Okay, thank you.
Interesting talk, and we are open to questions and discussion.
Just one question on the chronology. When did van der Waarden leave Germany and go to Zurich?
Well, he didn't go from Germany to Zurich. After the war, he went to Holland and lived there under fairly miserable conditions. He worked for some petroleum company for a few years and then went to Zurich in which year? 1950, right, to University of Zurich. So there was this, okay, so the story is that the Amsterdam colleagues were prepared to give him a position at Amsterdam University. This was okayed by the faculty, but his appointment, the Queen of Holland refused to sign. So he never got an academic position in Holland after the war.
At one point, van der Waarden was not completely consistent with his Einführung in die algebraische Geometrie, since he uses one of the basic ideas of ideal theory, the ascending chain condition.
And why is this not consistent?
Yeah, in fact, it is ideal theory, but he uses.
Well, I guess one of the points I was trying to make is that van der Waarden, after all, was extremely flexible. And even though I was portraying sort of the way, the style in which the book was written as being very much like the Italian school, of course, in all of his papers through Algebra and Geometry also, he tries to write this style, but still supplying the algebraic foundations that he has, of course, up his sleeves. So it is, I mean, okay, he's just.
It is consistent because this ascending chain condition is in his first papers. So when you're trying to eliminate elimination theory.
No, what he means.
I'm speaking of the preface of the introduction.
Exactly, because in the introduction he says we don't need ideal theory anymore, but then he uses a bit of it in the book anyhow. Right. In that sense, it's inconsistent.
Do you know how much attention they paid to Van der Waerden?
Well,
for example, the story I told you of Montesquieu. Montesquieu is really a disciple of Weil in some sense.
yes.
And so I wonder how much of this attention to Van der Waerden came from that source.
So I already mentioned one thing, namely that the generic points were sort of taken up by everybody and used, and if when they referred to somebody, they referred to Van der Waerden for this. The other thing, of course, they needed some kind of theory of intersection multiplicities. And one of the authors that he was constantly looking at to trying to get ideas was Van der Waerden, except that in the end he didn't use, as far as I can understand the development, it's not completely clear to me actually. I haven't maybe done all the details in there, but in the end he sort of found his own way to do it. But he certainly was consulting Van der Waerden's papers for this, trying to find inspiration there. And he tried many, many different avenues to come to grips with this essential, but because that's what he needed, the positivity of the.
Do you know what definition Zariski offered back in? Zariski gave
definition for
the
what?
definition of intersection multiplicity. You quoted this. Severi, rather.
Oh, Severi.
I
That
missed
was Severi. That was Severi in 1933. Well, I know the paper. I cannot sum it up easily. It's a long winding.
I was struck at what Van der Waerden said about the German of today is that he's not very geometrical, or at least not as geometrical as the Italians. Now, that's not what Bieberbach wanted to hear about in German. I mean, do you think that Van der Waerden was aware of that when he wrote that?
Bieberbach's racist papers begin in November 33. The paper I was showing you was submitted on 10th of October 33. So there was no, Bieberbach had not spoken up yet in this way.
But apart from Bieberbach specifically, I mean, the German was supposed to be intuitive and geometrical.
I don't know. I don't know. It's just a piece of lingo. I mean, a piece of a formulation that I think was in the air, and which you can actually find in many documents at the time. And I don't think it lends itself.
And so I'm in the comfortable situation I can skip lots of generalities that Norbert just told you, so I can jump on right to Zariski and zoom into his approach to onto his rewriting of algebraic geometry, because this is what arithmetization is. It's one more effort to give new foundations to algebraic geometry, and it was initiated by Zariski in the late 1930s, and it was named by Zariski arithmetization too. So even if it's, once again, this effort is, foundational process is about giving new foundations by.
So once you've introduced these multiplier ideals, there are a lot of invariants that you can define, you can attach to an ideal. You can kind of just spew these things out. And some of them I think are well understood, some of them are at the moment less so. But I want to sort of start by showing you some that I kind of enjoy, though it's not exactly clear there. Definitely there should be more there than one knows at the moment. So let me again recall the setup. So X is a smooth, complex affine variety. And again, you can think of, there's really no loss in taking X to be affine space of dimension D. And we take some ideal A in the coordinate ring of X. And so we defined this morning these multiple, given a rational number C, we defined this morning these multiply ideals A with coefficient or weight C, multiply ideal of A with weight or coefficient C. So this is a new ideal. Okay. So the first thing I want to define is something that probably is pretty familiar. This is the so-called log canonical threshold of A. So I think that's a good place to start. So the so-called log canonical threshold of this ideal A is what? Well, we actually, this is something that we saw at the end of this morning, but we just didn't give it a name. Remember, the idea is that if you fix the ideal A, if the coefficient C is 0, then you get the whole ring, and as the coefficient C gets bigger, at a certain point the ideal becomes non-trivial. And that jumping point, that place where it first becomes non-trivial, is a log canonical threshold. So the log canonical threshold, I'll use this abbreviation LCT of A. Let me write this vertically. So it's the minimum of all C greater than 0, so that this multiplier ideal A of coefficient C is non-trivial. So it's the least weight that you can attach to A and pick up an integrability, a non-trivial integrability condition. It's not completely obvious that this is a min instead of an inf, so it is, or you can read inf there. So what's the intuition? Well, again, as if you think back to, we kind of did some examples at the end of this morning's lecture. The intuition is that this is kind of a numerical measure of the singularities of functions in A. The picture is that the worse the singularities, the smaller the weight is before you get a non-trivial multiplier ideal. So the intuition is that small values of the log canonical threshold correspond to weighty or nasty singularities of the functions f and a. So let me do some examples. We actually did the examples this morning. Let me just recall them. So the first thing we did is we looked at the log canonical threshold of the ideal s squared t squared. That was the ideal corresponding to a double point, and this was 2. This was 1. Then we computed at some length the log canonical threshold of this cuspy ideal, so s cubed t squared. And remember, this is 5/6. It's smaller than 1, reflecting the fact that the singularity is more interesting. And then at the very end of the lecture, I did the case of these kind of diagonal ideals. So if I take T1 to the M1 through TD to the MD, we had a formula for the multiplier ideal, and we saw that it's non-trivial exactly when this sort of breaking point is the sum of the reciprocals of the MIs. So in this case, it's 1/3 plus 1/2 is 5/6. Okay. Now, these log canonical thresholds, as you may know, have been the focus of a lot of attention in algebraic and complex geometry. They're usually defined. They're usually defined in algebraic geometry in slightly different language in terms of singularities of pairs, which is where you can talk about a pair consisting of a variety and a divisor being log canonical, and this is the threshold of that happening. And they've also come up under different language in analytic geometry. They were considered by Arnold. Tézier told me this morning that I think this formula goes back to Hodge in one way or another. So, oh, okay, but these have a kind of a long history. Now, and actually a nice place to look, if you look at Collar's paper, Lectures in the Santa Cruz volume, there was Conference in Algebraic Geometry in 95, and there's a volume, he has a number of sections on how these log canonical thresholds come up in different branches of geometry. But now, see, if you think in terms of multiplier ideals, which for some reason, it's really natural not to sort of, if you think in terms of multiplier ideals, it's really natural to see this log canonical threshold as just the first in a whole sequence of invariants you can define. And the picture is you fix this ideal A, and then you let this C increase. And at a certain point, namely at the log canonical threshold, you pick up a non-trivial ideal. Well, why stop there? Keep going. So let's C get a little bit bigger. At a certain point, for a while, nothing will happen. And then you'll get you'll get a different ideal. And then you'll get a different ideal, and then you'll get a different ideal. So I want to sort of, this leads to what you might call the numbers, the jumping numbers. So those are where these ideals jump. So I want to sort of talk a little bit about them. So let me sort of formalize what I just said in a proposition definition. So if we're given this ideal A, there's a sequence, an increasing sequence of rational numbers Let's see, how am I going to index them? Okay, so I'm going to make 0 C sub 0 less than C1 less than, they go on forever. So that these multiplier ideals are A to the C, their intervals of constancy are, these are the boundaries of their intervals of constancy. So that these are constant exactly for, so the way they work is they're closed on the left and open on the right. So this is the shape. The intervals, the values of C where the multiplier ideal doesn't change happen to be closed on the left and open on the right. And so when you cross the boundary into the next one, your ideal goes down. And so naturally enough, these are called the jumping numbers. So these Ci equals Ci of A are what we're going to call the jumping numbers of A, or jumping coefficients. So the jumping numbers of A on X. So they're exactly the values, maybe it's easier if people see. They're the values of this they're the values of this parameter at which these ideals change. So what's the first one? This C1 is the, well, when you have coefficient 0, then the multiplier ideal is trivial. So C1 is the least value of C for which you get a non-trivial ideal. So this C1 is just the log canonical threshold. So the first jumping number is just the log canonical threshold of the ideal. So note C1 of this ideal